It's this ability to create a proof for any code. It's basically figuring out how to it's basically sort of, instead of checking each proof, what it's found is a way to take the. Okay. Great. So this week, the presentation I'm going to make is on hard problems in cryptocurrency. So in Ethereum, we've introduced quite a lot of new features, or rather new potential to the promise that cryptocurrency can bring. Instead of just being a simple system where you send money from A to B, you instead have this concept of contracts, where you can do not just currencies but also things like financial contracts, escrow contracts, encode any kind of rules for smart contracts. Send money conditionally from A to B under these circumstances, from A to C under other circumstances. But there's still a lot of things in cryptocurrency that we have not figured out how to solve. So what this presentation is going to be on is basically a list of the largest problems that are affecting the cryptocurrency space in general, including Ethereum, Bitcoin, and pretty much every other currency out there, and what some of the potential pathways might be towards solving them. So, in just 5 years, Bitcoin has gone from a white paper to a $7 billion economy with millions of participants. However, cryptocurrency technology is currently only still using very much elementary cryptography. The only crypto in Bitcoin is SHA-256 and ECDSA, both of which are technologies that have been around for 30 years. Pretty much everything in Bitcoin is potentially known by even quite a lot of people in high school. So, meanwhile, however, over the past 20 years, the world of cryptography has advanced by a lot. We have concepts such as zero-knowledge proofs, concepts identity-based encryption, pairing-based cryptography. Very recently, we've been starting to work on homomorphic encryption, fully homomorphic encryption, secure computational integrity and privacy, obfuscation. So there have been a lot of developments that have happened in the past 20 years, and developments that are still on the horizon today. And the reality is that if a lot of these advancements could be introduced into the cryptocurrency world, it could actually, all of the blockchains that we use could become thousands or even hundreds of thousands of times more efficient. And there are also other problems with Bitcoin. So, for example, there is a lot of economic issues that still go unresolved. The price is volatile. The fees are still, we don't know what to do with them. So the question is, what can we do about some of the issues that we have? So first problem with Bitcoin, scalability. So the problem here is that there's a common idea that Bitcoin can only support 7 transactions per second. So this claim is basically justified by the fact that inside of the Bitcoin protocol source code, there is a hard limit on the block size, which states that blocks cannot grow to more than 1 megabyte. Now, I'm calling this a myth because the reality is, if the number of transactions that pass through the Bitcoin system ever start to approach 1 megabyte, it's very trivial to remove the limit. All it takes is just releasing an update with a few lines of code removed. However, there is a reason why the limit was put in, and there's a reason why we can't just say that we can just put as many transactions into Bitcoin as we want. So the problem is basically it's a trade-off. It's a matter of scale versus decentralization. So right now in Bitcoin, every block has 150 kilobytes. Those 150 kilobytes are roughly 500 transactions. So the block 6 blocks an hour, so the blockchain grows by about 1 megabyte per hour. Currently, I believe it's somewhere between 10 to 20 gigabytes. However, what happens if Bitcoin turns into a mainstream payment system? Well, let's take an existing mainstream payment system, MasterCard. 2,000 transactions a second. So what happens if you have 2,000 transactions a second? Each transaction is 150 bytes, 300 kilobytes a second. The blockchain grows by 1 megabyte every 3 seconds. There are a lot of people in the world that don't even have the bandwidth to download that, or much less the CPU time to process it, and much less the hard disk space to store that entire thing. So if Bitcoin grows to the size of MasterCard, only large businesses will be able to run full nodes. And there's a pretty interesting statistic that even though Bitcoin has been growing dramatically in the past 2 years, the number of Bitcoin nodes has actually stayed pretty constant. It's been somewhere between 1 and 20,000 the whole time. And the reason is that even as Bitcoin becomes more popular and more people are interested, the prospect of running an actual full node becomes more and more difficult with every passing month. So what happens if Bitcoin grows to become even bigger, and let's say at some point there's only 100 full nodes? Well, in that case, there's 100 players. 100 players can very easily conspire, and they can basically agree, okay, let's make a block where instead of just giving ourselves a 25 BTC reward, we give ourselves a 20,000 BTC reward. Here's the problem with that. It might sound like that's something that's incredibly easy to catch, but the thing is that in Bitcoin blocks, there's this concept of mining fees, where in every block, the miner gets the 25 BTC reward plus all of the transaction fees from all the transactions. So in reality, if a block comes out that gives the miner 25,000 BTC, the only way to prove that that block is illegitimate is basically by scanning through each and every transaction and processing the entire block. So problem is, okay, let's say we have a ecosystem where there's 100 full nodes, everybody else is running a light node, and then those 100 full nodes agree, we're going to start pushing out blocks, giving ourselves 25,000 Bitcoins. The light nodes have no immediate way of realizing that anything is wrong at all. They just think, oh cool, I received the block with 24,975 Bitcoins worth of fees for some reason. There was a transaction with 200 Bitcoins in fees before. Why not 24,000? So eventually, of course, somebody's going to notice that something's wrong, and there's going to be a whole bunch of posts on the forums about how there's a malicious block in the blockchain, and there might be a movement to try to blacklist that particular block, but by then it may well be too late. So the root of the problem is basically that if someone wants to create this kind of takeover attack on the network, the ability to detect the fraud has to be built into the protocol at the lowest level, and light nodes don't have a way of doing that. So, what are the solutions? So there's several different ideas. So one idea is there are a few tricks that you can add into the blockchain to make light nodes more powerful. So in Bitcoin, it's basically a matter of embedding transaction fees into the Merkle tree at each step. So you would actually be able to say, yeah, this node over here is where the miner tried to introduce extra fees that came out of nowhere. And in Ethereum, the equivalent strategy is to basically have each block store not just the initial state and the final state, but also the root of every single intermediate state. And so if there's one honest node somewhere processing all the blocks, and it notices that a certain block has an inconsistency in some place, it can warn everyone else, and it would be up to the miner to actually to construct a cryptographic proof saying, yeah, look at this subset of the blockchain, and I can actually show you that this particular part of the block processing is actually valid. So that's one approach. So what are the problems with it? Well, it works. Now, it's not fully decentralized, so we're still not breaking through the fundamental problem that every single node on the blockchain has to be processed, or every single full node has to be processing every single transaction. So even though you have 100 nodes which can potentially audit each other, you still have only 100 nodes in the blockchain. Idea number 2. So let's put the block, instead of storing the blockchain locally, what we can do is we can store the blockchain in the cloud. So obvious problem with that is time. So if it takes you 2 seconds to process every single transaction because you have to download a few extra parts of the blockchain, that's obviously not going to be viable. Now, fortunately, in general, we know that systems in general and blockchains too follow these Pareto laws. So we know that 20%, it's very likely that 20% of the blockchain is used is being used 80% of the time, or even that 3% of the blockchain is being used by 97% of transactions. So if we have that kind of distribution, the problem actually gets simpler. What we do is we identify the 5% of the blockchain that's being used the most often, and then we take that 5%, we store it locally. You know, you can even do multi-level caching. You can even say store 1% in RAM, store 10% on the hard drive, and then store the other 90% on the internet. So what kind of data structure is stored on the internet? Well, we already have this concept called a distributed hash table. It's something that's used by BitTorrent. It's basically sort of this worldwide distributed database that can store any number of what are basically key value pairs. And so since that's what the blockchain basically is, you know, why not just use the DHT to store the blockchain? So there's a project called GFS, the Galactic Cloud System, which actually a guy in Menlo Park is developing, which might be able to do that. Or alternatively, you could just use the Ethereum protocol. So the idea there would be, by default, every full node might say store the top 10, the most frequent 10% of the blockchain locally, and some other random 5%. And then if you want some node from the other 90%, you would just make a query on the network, and eventually and very likely somebody's going to come back with a response. So it's an approach. It could work. Problems are obviously it's still slow, and there might also be possible issues with consensus. So for example, what if some parts of the blockchain are reachable to some nodes but not reachable to other nodes? Then you might have the issue that what if some full nodes are basically returned with an error because they can't fully process a certain block and think it's invalid, but then other nodes think that the block is valid. So it's not insurmountable, but it is something that's going to need a lot of work. Other problem is, so then the third idea is probably the most ambitious. Let's actually solve the problem that the blockchain has to store every transaction. Instead, what we do is we have multiple blockchains. So we could have 10 blockchains, we could have 64 blockchains, we could have 2,000 blockchains. And the rule is that each of those blockchains have their own contracts, they have their own transactions, they have their own balances. But the blockchains are merge mined. So what that means is that the miners don't actually mine one blockchain. The miners might mine, say, 4 or 5 different blockchains that are close to each other by some metric of distance that we define. And then what we say is that we sort of cover the entire blockchain with a bunch of these small little pools that each of which are covered by specific miners. And the idea is that the whole thing is going to sort of grow over time. It will grow. The blockchain is not going to grow perfectly in sync, but it will. But each of the overlapping pieces will essentially still reinforce each other. So, and then in order to make sure that the ether in chain 1 has the same value as ether in chain 2, what you would end up doing is you would end up introducing a cross-chain swap protocol. So if you're merge mining between, say, blockchain A, B, and C, one of the allowed transaction types would be to destroy an ether in chain B and create an ether in chain A. So it's potentially an incredibly powerful idea because it actually solves the underlying problem. It allows a blockchain architecture to exist without every node needing to store more than 1% of transactions, 0.1% of transactions. You could go as low as you want. Transaction fees could drop by a factor of a few hundred. Problem is though is that first of all there are potential consensus issues. Also, contract coding gets more complicated. So if we're going to have custom currencies on the blockchain, how do custom currencies work? Does each custom currency need a swap protocol, for example? And also the architecture is completely untested. So we've been working with blockchains for 5 years, but this idea of multiple blockchains, I don't think we even have simulations at this point. So next problem is this thorny issue of mining centralization. So originally, back in 2009 and 2010, mining was pretty much entirely done on your desktop. You download a program, you click mine, and you mine. Any kind of computer, and you'd be guaranteed to get 50 BTC eventually, whether it's in a few hours or a few days. In 2010, however, people came out with GPU miners. They came software which was able to use graphics processing units, GPUs, which are basically hardware chips that are used in really powerful computers to do things like video processing and gaming, and they're able to use them to basically to mine about 50 times faster than CPUs can. So at that point, actually, you could see on the difficulty charts, the Bitcoin difficulty shot up by a factor of about 100 over the course of maybe about half a year. So that's what the status quo looked like at the end of 2011. At the end of 2011, mining with a CPU was basically non-viable. 2012 kept on going. In 2012, actually, people came up with this concept of mining on FPGAs. An FPGA is called a field programmable gate array. It's basically this interesting kind of chip which is actually even more specialized. But the idea is that you can sort of when the chip is shut down, you can sort of reprogram it, and you can actually change some of the gates around, and you can create sort of semi-specialized circuits for Bitcoin mining, which can potentially be even faster than a GPU. Now, FPGA technology actually never really got very far because in 2013 we saw ASIC miners. ASIC stands for Application-Specific Integrated Circuit, and it is exactly what the name suggests. It's an integrated circuit that's specifically designed for the sole application of mining Bitcoins. So companies like Butterfly Labs were and still are creating these little mining boxes whose sole purpose is to crank out billions of SHA-256 computations a second. And the only way that you can mine is basically to buy these devices from the companies. That's the status quo today. Where I think the status quo is going to be in 2 years is that because it's so inefficient to actually ship these mining boxes, instead people who want to participate in mining are basically going to purchase mining contracts, and the mining itself will be done in centralized facilities. So, not really a very democratic currency system, where you need $10 million of capital in order to produce an ASIC fab in order to actually get any Bitcoins for mining. So the challenge here is, how do we come up with a proof of work algorithm that fixes these issues? I mean, the fact is that the problem here is that SHA-256 is so easy to optimize with specialized hardware. Is it possible to create a proof of work which is harder to optimize with specialized hardware? And there's another problem, mining pools. So this also came about basically when ASICS started really coming into play. Programming language, EVM code. So this will basically consist of picking out random transactions, interpret and running them, and then finally after running about 16 of these contracts, you would just do a SHA-3 at the end, and just like Bitcoin mining. So just the algorithm itself is just, once again, take the state about 16 blocks ago, pick a few transactions, execute them onto the state, see what the state is at the end, SHA-3 the result, and just like Bitcoin, if the result is lower than 2 to the 256 divided by the difficulty, then you have a valid block. So the point of all this is that basically the point of mining in general, it's a proof of work, right? It's just basic work that you have to do in order to prove that you have access to a certain amount of computational resources. So in Bitcoin, that basic work is just SHA-256. Here, that basic work is actually processing a few transactions and then doing SHA-3 at the end for cryptographic security. So what are the advantages of this approach? So first of all, yes, in order to make an ASIC for this kind of mining algorithm, you would need to make an ASIC for interpreting EVM code. EVM is Turing complete. Therefore, EVM can potentially encode arbitrary computations. Guess what an ASIC for an application-specific integrated circuits for arbitrary computations is called? It's called a CPU. So that's the idea. The other advantage is that you actually need the entire blockchain to mine. Because you're grabbing random contracts and those contracts are grabbing random data, it's not going to be possible to just download the block header from some mining pool. Every single miner would actually have to have a local copy of the blockchain themselves. And so theoretically, they could just grab parts of the blockchain from the internet if they need to, but that's going to slow the process of mining down by a factor of 2,000. So in theory, we've solved both problems. We've solved the first problem by requiring the blockchain to be stored locally, and we've solved the second problem by making the mining algorithm Turing complete. Problems. So first problem is, optimization. So first of all, the algorithm that I described above, where you just pick random transactions, you execute them. The issue is that most of the transactions are going to be independent, and so what you could do is you could just pre-process every single transaction, figure out what impact each transaction is going to have on the state, cache that, and then you just apply all the transformations one after the other. Then, another idea that we had is, well, what if we modify some of the contracts a bit? Even still, what if there's some way to create sort of semi-specialized modules that would only do that would theoretically RCP use, but at the same time have incredibly optimized components for certain specific parts of EVM code. Another problem with the algorithm is basically a long-range 51% attacks. So the idea is, okay, if you want to make a 51% attack, you don't go 6 blocks back, you go 1,000 blocks back. Then you process, you go through 16 blocks, but in those 16 blocks, you include transactions that you're very good at processing. So they might be basically obfuscated loops. So something which any other miner is not going to be able to optimize easily, but which you can just do in an instant, and you know what the final result is. So then once those 16 blocks have passed, you're basically mining your own contracts. And even if you have like 1 or 2% hash power, you might be able to eventually overtake the network. So in general, solution to both of these problems is somehow randomize the transaction code. But the big problem is, how do we randomize? Will the process of executing random code just end up with something that just stops after about 5 steps? Or will it actually produce work that's interesting? We don't know. It'll take a lot of research to find out. Problem 3. So another problem with Bitcoin mining is that it's useless. Basically, you have these hundreds of thousands of specialized hardware boxes all around the world, cranking out billions of SHA-256 computations every second. And reality is those computations have pretty much no social value beyond propping up the Bitcoin network itself. So if the Bitcoin system was centralized, then it could avoid all the extra work, and it would all just, and I think there was even a statistic at some point that the Bitcoin network currently spends something like $30 of effort for every transaction. Now, obviously, that is going to decrease as the mining reward decreases, but at the same, and it's also going to decrease as the transaction volume goes up. But even still, what if we can actually do something with all that computational effort? So the first coin that actually attempted to solve the problem was Primecoin. So the idea with Primecoin is, well, let's make the mining algorithm not just some boring SHA-256, but let's make it something that's actually useful to society. So the canonical example is something like Folding at Home, where basically Folding at Home is a computer program that you download that basically does protein folding simulations. And the theory is that these simulations are actually, the results of these simulations are actually valuable in medical research. So, problem is, of course, the prime number sequences aren't really that useful. And even if they are, once we start spending billions of dollars on them, all of the utility will probably be sucked out in the first few months, and then there's not going to be much point in finding any more of them. So why is Primecoin using prime number sequences? Why isn't it using Folding at Home? And the problem is that proof of work functions have to be easy to verify. Proof of work. So with SHA-256 is that sure. The way the mining algorithm works, you just crank out billions of hashes until eventually one of them produces a result that looks good. But the process of figuring out whether that result looks good takes a few microseconds. With Folding at Home, if you do around the Folding at Home, the only way to actually prove that the round is provided a good result is by repeating the entire round yourself. So verification is exactly as hard as the mining process. So that's basically one of the challenges here. Is it possible to create a type of computation, whether it's in medical computing, scientific computing, astronomical computing? One interesting idea is weather prediction. Is it possible to create some kind of work function, which both has this property that it's actually easy to verify, but is also actually useful? Now finally, here's another interesting point. Right now, maybe I would argue that at least half of the cost of Bitcoin mining, of developing Bitcoin mining ASICs, is actually the cost of research. The cost of developing, figuring out better algorithms for the chips. So what if, even if the work itself is useless, the kinds of hardware research that it requires is useful. So in the context of Primecoin, arguably we have that to some extent. Figuring out how to make ASICs for Primecoin would basically is the same thing as figuring out how to make chips that can do arithmetic with large numbers efficiently. And arithmetic with large numbers is useful. It's very useful in cryptography. It's useful in scientific computation. So if we figure out how to, say, multiply two 10,000 digit numbers in hardware very, very fast, and that happens because of Primecoin, then maybe Primecoin wasn't so useless after all. Problem 4, price stability. So this is where we get into some of the economic issues. So Bitcoin has a rule that there's never going to be any more than 21 million Bitcoins out there. So the way that works is, for the first 4 years, the mining algorithm gives out 50 BTC to the miner every 10 minutes. The next 4 years, the mining algorithm gives out 25 BTC per 10 minutes, then 6.25 per 10 minutes, then 3.125 per 10 minutes, then 1.565, and so forth. Until eventually, around something like the year 2110, there's not going to be any more Bitcoins given out at all. Mining is just going to be funded entirely by transaction fees. With Ethereum, we have a somewhat less deflationary model. We're saying there's some initial supply, and there's going to be permanently linear supply growth. So if there's 10 million coins initially, then after 1 year there's going to be 13 million, then 16 million, then 19 million. After 100 years there's going to be 31 million, or rather 310 million, and so forth. So problem is, however, both of those formulas are pretty crude. So in both of those cases, in Bitcoin, there's going to be 21 million Bitcoins if Bitcoin fades into obscurity and just becomes a tiny currency used by some small niche subset of the population. And there's going to be 21 million of them to become the reserve currency of the world. With Ethereum, same thing. I mean, the linear supply growth is going to be less wrong because simply by looking at Ethereum's expected growth curve, but it's still not going to be anything close to perfect. So what if we can make a currency whose supply is whose supply is actually dependent on the demand? So right now, the demand is volatile, but the supply is fixed. So obviously the price is going to be volatile. That's basically the reason why the price jumps up by a factor of 10, then it goes down by a factor of 2. Bitcoin's entire price right now is basically predicated on the small probability that it's going to be much larger than it is now. What if you can create a currency such that if the currency grows, then the supply grows too, and so the price doesn't change all that much either way? So there's 2 ways to approach that ideal. One way is to say, let's measure price. So let's have a formula let's have a currency that is somehow crypto-magically aware of what its price is. And if the price goes up, then the currency pumps out more units of itself. So, problem is, how do you measure price? One approach is to measure the difficulty. So the argument is that if Bitcoins get twice as valuable, then there's going to be twice as much incentive to mine, and so there's going to be twice as many people interested in mining in the equilibrium, and then the difficulty is going to go up by a factor of 2. So let's use difficulty as a proxy of price. Problem with that, however, is that there's no way to separate price increases from technological advancement. So Moore's law, computers get twice as powerful every 2 years. So if we use this as a formula, then what happens is basically that we have 100% inflation every 2 years. 41% inflation, I'm pretty sure that's one of the things that cryptocurrency people are trying to get away from. Now, obviously, you could use a few heuristic formulas. Like you could just assume that Moore's law is going to have. You could try and guess that Moore's law is going to be 100% per 2 years, and it doesn't look like it's going to accelerate past that anytime soon. And then you sort of subtract that out. But even still, that's you're creating a formula with a lot of instability. The other approach is let's measure demand. So let's have a currency that crypto magically knows how popular it is. And then if the currency becomes more popular, then we increase the supply. This is just another way of approaching the problem. So problem there is, however, how do you measure demand? So there's a few obvious heuristics. Number of transactions, number of distinct miners, number of nodes, number of distinct addresses. And but the problem with all of those is that there's always going to be malicious actors. So if I'm a miner, I'm going to want the supply growth to be as much as possible. If I don't have any currency units, I'm going to want the supply growth to be as much as possible. If I'm in debt, I'm going to want the supply growth to be as much as possible in order to drive down the price. Potentially, I could even put up my if Bitcoin was subject to this kind of system, I could put my Bitcoins up at Bitfinex, short Bitcoin at 10x leverage, so I would gain $10 for every $1 that the Bitcoin price fell, and then I would try and basically flood the entire network with a lot of transactions, make a lot of new miners, all with their own public keys, turn on my botnet, get another million nodes into the network, and then try and make the network think that it suddenly got 100 times more popular. And then suddenly it's going to release 100 times more units. The price is going to drop down from 550 to say 55. Guess what? I've just earned $4,500 times whatever. So problem is basically how do you create a system that's immune to that kind of manipulation? Also another problem. So suppose you can actually accurately determine the price of a crypto asset in USD. Here's the problem. We figured out how to be stable in the upward direction. And that actually does by itself give us a lot of stability in the downward direction. Because the reality is that when the price goes down, quite often it's because the chance that the price will massively go up has suddenly been taken away to some extent. So on some level, just having a guard against upward price increases actually also gives you a guard against downward price increases. But what if we want better assurances? What if we want what if we want to be secure in the knowledge that the price of the asset is going to remain the same even if interest goes down drastically? The issue is, of course, that issuance cannot drop below zero. So if there's 37 million coins out there, and let's say 1 million coins get produced every month, but then the system gets less popular. 500,000 coins a month, less popular. 100,000 coins a month, less popular. 0 coins a month, can't go below zero. But then even if there's a fixed supply, the price might still fall, and then you don't really have the currency doesn't really have any monetary policy tools beyond that. So one solution with that is basically, let's have a currency whose total supply is 0. So that sounds crazy, but in reality it's actually doable. So the trick is you basically use financial derivatives. So what you do is, let's say you have an asset, which is called, so we have two assets. One asset is going to maintain a value at 1 USD. Another asset is going to maintain a value of some number of Ether minus 1 USD. So the idea here is that the contract is actually going to try and balance itself in such a way that its USD liability is going to be around 0. And then if the USD liability is too high, the contract is going to set a negative interest rate on USD. If the USD liability is too low, then the contract is going to encourage people to get more, withdraw some of their USD and so forth. So there'll be a system which sort of balances between these two different assets and tries to make sure that the number of USD that the contract has to give out is always around 0. Now, obviously, in order for this to work, you do need another asset to measure against. So in this case, I'm using Ether, but in general, some crypto asset has to exist, and there's always, assuming that the asset has an above 0 price, there's always going to be speculators that are interested in owning some shares of that asset. So those are basically some of the issues around price stability. Finally, here's another problem. Or rather, it's a solution. So another solution to the mining problem is, let's get rid of work entirely. And we have to ask ourselves, what's the point of having proof of work? So the point of having proof of work is basically to have a mechanism in order to prevent Sybil attacks. So a Sybil attack is, well, I turned on my botnet, I have 1 million nodes, and I flood them in the tiny Bitcoin network. And each of those nodes is going to claim that I have $1 million. How would the Bitcoin network be able to tell that all those statements aren't legitimate. How's the Bitcoin network going to be able to ward off that kind of attack? So the way Bitcoin works is that instead of measuring nodes by the number of nodes, it actually measures nodes by the CPU power that they have. That's once again the concept of mining. That's the concept of proof of work. So every mining node on the network has to do all these proof of work computations, and so eventually, and so in theory, at all times, attackers are not going to be able to amass more than 50% of the total network hash power. So what proof of stake says is, well, let's not use computational power for that purpose. Instead, let's use currency units. So if you create a block and if you sign that block with the private key that also owns a whole bunch of currency units, then that's also a form of scarcity. That's also something that attackers can't just easily amass with a botnet. So the algorithm here that I'm describing, you basically take the hash for every single transaction output. Every second, you take the hash of the previous block, the output, and the timestamp, and you check if it's lower than some target multiplied by the value of the output. So what's the point of this? So every single transaction output has some chance every second of becoming a valid signer for a block. However, that chance is actually proportional to its value. So if you have a 10 BTC output, you have 10 times as much of a chance as if you had a 1 BTC output. If you have 10 1 BTC outputs, then you also have 10 times as much chance because the algorithm processes each of them separately. So the idea is that you're sort of replicating the concept of proof of work, except instead of voting with your CPU power, instead of having actual mining rigs that use CPU power, you have simulated mining rigs that use currency. So what are the problems of proof of stake? So here's one problem. In proof of stake, there's this idea that there's nothing at stake. So once again, what's the point of proof of work, proof of stake, proof of anything algorithms? Basically, if there's a blockchain, there's a fork in the blockchain, you have to have some algorithm for deciding which fork is legitimate. So if there's a transaction in this fork where I sent $100 to Bob, and this fork where I sent those $100 to Charlie, both of those can't be correct because I only have $100. So which of those forks is going to take precedence? In proof of work, it's basically a voting system where you vote with your CPU power. Every single miner has to choose, do I mine on this fork or do I mine on that fork? In proof of stake, however, it's a bit different because, well, guess what? When the fork happens, I have money on this fork, I have money on that fork. On this fork, I have a choice to mine or not to mine. On this fork, I also have a choice to mine or not to mine. The optimal strategy for me is actually to mine on every single fork because all the mining is independent. So in that case, suppose that I'm an attacker. So I send 1,000 Bitcoins to you. Then I create a new fork. That fork was just before that transaction, or just before the block where that transaction got confirmed. And then I send those 2,000 Bitcoins back to myself instead. And then I publish that fork. So there's two forks of the blockchain. One of those forks is going to be a pretty long fork that has me sending 2,000 Bitcoins to you. And there's going to be another fork with me sending 2,000 Bitcoins to myself. Now I publish that fork. So there's two forks out there. Now there's two pools of stake. There's my pool of stake, let's say something like 1%, and then there's the network's pool of stake. Now the network, every participant in the network has the incentive to mine on both chains, and really to mine on any chain that comes up. So the rest of the network is just gonna mine on this chain, so the rest of the network's contribution to both chains is gonna be equal. Myself, I'm gonna mine just on my chain. So my chain is actually gonna grow 1% faster than the other chain. So then, after a few thousand, both chains are gonna continue growing in parallel, and eventually after a few thousand blocks, my chain is actually gonna be the longer one. Guess what? In the version of the blockchain that's called the truth, I never sent those 2,000 Bitcoins to you. So I basically just reversed the transaction. 2 months ago, I created an algorithm called Slasher, which basically fixes the problem. So here's how Slasher does it. So first of all, you determine miners for each block ahead of time. Then you have a rule that says, if you get caught mining on 2 different chains, then what you can do is you can actually take a proof that you can actually take the block that you mined in the second chain, and you can import it into the first chain, and that block just serves as a proof that you double mined. And if you double mine, then you lose the mining reward. So there's so after you mine, there's a period of 1,000 blocks before you can actually claim your reward. And during that period, if anyone else submits a proof that you actually mined on another blockchain at the same time, then you lose your reward, and they get some small portion of your reward as a reward for themselves for ratting you out. So the point of this is that now double mining is impossible. There is no option to mine on this chain and to mine on that chain. And so you have to mine on one of them. So that fixes the problem. However, Slasher does have one issue, which is because miners are decided ahead of time, and miners do have, the issue is that miners actually have to be decided ahead of time, because if you decide all the miners stochastically, then you have the problem is that during each block, there's only a small chance that each individual node is going to be a miner. So if you double mine, that's not actually ever going to be visible as double mining. If the decision is independent, then chances are, most of the time, you're obviously not going to get it. You're not going to get a block on either of the chains. But maybe 1% of the time, you're going to have an opportunity on this chain and no opportunity on that chain. Or an opportunity on this chain and no opportunities on that chain. And only 0.01% of the time, you're going to have an opportunity on both chains. So the optimal algorithm would be, in the second case, you would obviously just mine on the chain that you think is the longest. But in the first case, you would just take what you can get. So once again, so the problem with that is, so basically it completely negates the whole concept of punishment, and you can mine on all the chains again. So that's the reason why you have to decide who the miners are going to be beforehand. And when you have that and there's a fork, then during each block, every single miner is either going to have a chance to mine on all the chains or have a chance to mine on no chain. So every time there's an opportunity to mine, there has to be a choice to pick one of the forks. So the problem with that is that because the miners are chosen far ahead of time, they can collude. 64 miners can get together and they can say, none of us are going to actually publish block number 3845 unless people in the network give us $200,000. They can basically hold the entire network for ransom. Potentially, those miners can even collude to do double spending attacks. So, challenge is there some way to take some of these ideas, or to take different ideas, and do better than Slasher, and do better than the proof of stake algorithm found in PP coin and all the other ones. It's a research problem. Now we get to another set of problems in the economy. So the issue here is distribution. So who do the currency units go to? So in Bitcoin, the currency units will go to miners. In theory, back in 2009, 2010, you download a computer program onto your desktop, you run it, and eventually you get 50 Bitcoins. And then maybe 100 Bitcoins, and maybe 150 Bitcoins. Problem with that, however, is that if you look at what happens now, there's an entire industry composed of both hobbyists and professional firms dedicated to grabbing together the best hardware possible in order to mine, and doing it pretty much immediately. ASIC manufacturing firms. So theoretically, if you want a distribution mechanism just for the short term, then you can come up with some clever new form of cryptography that no one's figured out how to specialize yet, and maybe you can come up with a reasonably fair distribution model. However, if you want something that lasts in the long term, then eventually there's going to be ASICs, and so your currency might really, I think in 2 to 5 years, there is a risk that Bitcoin is just going to turn into a welfare program for AMD and Intel. So that's maybe a reason why it's actually a good thing that Bitcoin has a $21 million supply cap, and 75% of the Bitcoins are already gone. Or rather, 75% of the Bitcoins will be gone by 2016. Because if this wasn't the case, and Bitcoin had a linear supply model, then, yeah. So, the problem is, though, is that if currency units are not distributed to miners, who else? So, this is the ultimate ideal, obviously. Can we create a currency where every person in the world gets some number of units? So there's a lot of coins already that already try to implement that. So for example, we've all heard of Aurora coin in Iceland. Basically, they're handing out 31 units to every Icelandic citizen. There's an equivalent experiment in Spain coin, equivalent in Spain called Spain coin. There's also Mathcoin, which is some Native American tribe. And most recently, there's Aphrodite coin in Cyprus. So all of these try to say, okay, every citizen gets some number of coins. Problem with that, though, is, first of all, the mechanism has to continue to work in the long term. So all of these are one-offs. They're just finite supply currencies. There's a 50% or 75% free mined that's distributed to everyone, and then the remaining 25% gets mined. Ideally, this kind of a system would keep on giving units to people in the long term. You know, we want a financial system that keeps on giving people at least some amount of resources to survive, even after the system gets created. You know, what are the people who are born in 2020 going to do? So there's three ways of solving the problem that we know of. One way is to have a trusted third party. So this is actually how Aurora coin and Mathcoin and Aphrodite coin and Spain coin all work. Basically, you'd have to prove that not Mathcoin. You have to prove that you are part of the set of people that's entitled to get a coin, whether you're an Icelandic citizen, a Cyprus citizen, or a Spain citizen, by digitally signing a message with your passport. And as it turns out, some of these new passports actually have just enough cryptographic hardware in them to make this sort of thing possible. So passports contain chips which are digitally signed by some passport issuing agency. And then if you can submit your passport, then you have some number of tokens. So biggest problem with that, obviously, is, well, there's a trusted third party. If the government decides it wants to inflate Spain coin, then the Spanish government can just print out a few billion passports and keep them in-house. So idea number two is, can we create a proof of work that's somehow dominated by human labor? So the idea here is it's not quite the same. You don't just give out units to people for free, but instead you have a proof of work where you actually have to do stuff by hand in order to solve the problem. So we already know of the concept of a CAPTCHA, where every time you sign up for an account, then you have to basically look at a few numbers, try and figure out what the numbers and letters are. What if we can come up with something like that but better? So if we do that, then we basically, what we end up doing is giving some kind of job to everyone in the world. Imagine every single person in the world having a guaranteed job, even if it's like $1 an hour. You might laugh, but inverted or entity is an actual person and not some bot. It already exists within the community. I know that each and every one of you are actual distinct human beings, and for every single person in the world, at least some number of people know that for them. So is there some kind of algorithm that can somehow take that knowledge and aggregate that knowledge and trying to figure out some way of figuring out who all of the individual humans are and hand the shares out? So 3 different ideas. So human labor-based proof of work. This is something I want to sort of expand into a lot because it's a very interesting problem all by itself, right? So once again, CAPTCHAs are the best thing that we know of so far. Also, there's the various different strategy games. So chess, for example, computers are quite good at playing now. They're better than humans. But there are other strategy games, like Go, for example, where in Go, humans still remain slightly better than computers. And I believe there's also some AI researchers that actually made a game that's deliberately as hard as possible for a computer to beat humans at. So the challenge is, is it possible to take one of these ideas and turn it into a proof of work sort of task that the average human can do competitively? So, yes.
Maybe we need to consider that some countries, they will use slave labor and things like that to do your jobs.
Right. It is possible, right? So the issue. Yeah. Yes, it does. But I suppose slavery is something that the world needs to address in any case, and Yeah. So, right. So, but the basic argument here is, so yes, it does happen in things like gold farming, but the argument is that if you make it economically, yes.
What about Hunter coin for this purpose?
Yes, right. Hunter coin is excellent idea. I'm not sure exactly how secure it is, so it's a matter of security. Right. So the economic argument basically is that if you can come up with some kind of task that requires no infrastructure whatsoever, that everyone can do just by themselves, then there's no incentive to actually centralize it. So that's also part of the challenge, right? It's like if it's some kind of task that you need, that you need people, but you also need some specific set of infrastructure, then yes, you are going to create the equivalent of a Chinese gold mining farm. But is there some way to do better? So once again, this problem may turn out to be impossible to do practically. Still worth thinking about. Proof of excellence. So this is another approach. So it's a distribution model that rewards working on research problems. So idea here is that there are a lot of research problems that are actually hard to do and require humans to do them. Now this is different from human labor proof of work because it's not anyone that can work. You need a lot of skill. You need to be a very skilled academic in order to solve the problem. But at the same time, these are things that people can do and which are actually useful, but which computers can easily verify. So one example of this in reality is there's the RSA factoring challenges. There's math challenges for finding large prime numbers, and there's people who have been working on those challenges, and there are rewards for them, like tens or hundreds of thousands of dollars. And this is sort of research that's obviously very valuable. And the nice thing is it's computationally verifiable. If you can come up with a really large prime number, there's an algorithm in order to figure out if it's actually prime. Another interesting idea is this concept of proof of proof. So this basically you generate mathematical theorems, and then you would check, and then you would just put them out there. And if you can come up with a proof, then you would encode your proof in such a way that the computer can check it, and if your proof checks out, then you win. So the problem with all of these is basically egalitarianism. So in terms of math puzzles in general, we can count on the back of our hands that there's always a few mathematicians that are really good at them. So the problem is basically, if we come up with this kind of system, will Terry Tao end up taking 10% of the entire world's GDP? I suppose it's better than the banking system taking 10% of the world's GDP, but still not perfect. So the general way that it would work is, so there's already a concept of so-called automatic proof assistance. So what a mathematical proof is, it's basically a series of steps in some. So a proof is basically a series of statements where each statement can be very trivially deduced from the previous statement. So if you remember back when you were in high school and you had to do various different things like simplifying and expanding and factoring in algebra, what you would do is you would make a series of steps, and it would be very simple to figure out whether each step was a legitimate consequence of the previous. So then so what COP does, it's an automatic proof assistance software where you would put in a series of statements. It would check at each level whether each statement is a valid consequence of the previous one. And then and in that way, it would check if the entire proof is legitimate. So the idea is that if you want to come up with this kind of model, we would generate some statements in second-order logic or whatever other language. So if you want to make this actually useful, one of the ways that we can target usefulness is by sort of specializing a language. And then reward proofs. So problem is most proofs are trivial, some are interesting, some take years to do. So one solution is that first of all, you put the responsibilities on the miners themselves not to make trivial proofs, or not to make trivially provable statements. So alongside a statement, miners would have to actually submit a deposit. If the statement is solved very quickly, the deposit is forfeited. Otherwise, what you would do is you would say the reward for submitting a proof to some statement is proportional to the amount of time that it goes unsolved. So even the really big proofs that go unsolved for 2 years, those just become even more valuable. So some theorems are going to be proved by ASICS in a few hours, some by normal computers in a few days, and then some by actual people in weeks and months. So, this just basically pays for every single math research department in the world. Problem number 8, timestamping. So in Bitcoin, every block includes a timestamp. So every block includes a number that states when the block was created. And the rule is that a block is valid if the timestamp, if 2 conditions are met. So first of all, the timestamp has to exceed the parent's timestamp. So a block has to come after the previous block. And then the block has to come less than 2 hours ahead of the verifier's block. So if I'm verifying a block, I'm not going to accept it if it's more than 2 hours ahead from my point of view. So problem is, now in Bitcoin this is fine, because in Bitcoin time isn't really important from the point of view of each individual block. Because the time only matters in the context of difficulty adjustment, and that happens every 2016 blocks anyway. The difficulty adjustments are pretty tiny in any case. Or rather, each individual block's contribution to the difficulty adjustment is tiny. So, problem, though, is that if timestamping becomes more important, if you come up with a protocol that actually requires the network to know what the exact time is this really insider compatible? Is this really guaranteed to crypto consensus? So, for example, this proof of stake algorithm that I described, it actually has a critical vulnerability. The vulnerability is there's no incentive for people to be honest about the timestamp. If I'm a stakeholder, I'm going to want to try all the timestamps up to 2 hours into the future. So that way I have 7,200 times as much chance to actually make a valid block. So, and the problem there is that assuming in the equilibrium, every miner is going to do this, and if every miner does this, then is the consensus going to be stable? Because at that point, your bottleneck isn't even the proof of work or proof of stake system. Your bottleneck is this timestamping system. The entire security of the blockchain falls onto this sort of consensus mechanism. So, is this really stable? Probably not. And obviously, problem 2: can we do better than 2 hours of accuracy? So, I think the mechanism that we have can probably go down to maybe 10 minutes or 5 minutes. Can we make it go down to like 30 seconds or so? Solution? We don't know. I know there have been quite a few people already trying to solve the problem. Another problem is, well, this isn't even a problem, it's also an opportunity. So this is something that people have been working on for about 2 years. So the idea here is that this is called succinct computational integrity and privacy. It's an algorithm where if you run a program, you can come up with a proof that you ran that program and you got a certain output. So there's quite a few interesting applications of that, but in general the algorithm is, first of all, you turn your program into what's called a circuit. So you unroll all the loops, you flatten the program out, extend it to whatever number of computational steps you need. Then you run the circuit and you store the circuit execution trace. You store the state of the program at each step. So then there's this somewhat crazy math where you would create a function that you would check if each state is a successor of the previous state. This is exactly the same thing as a proof checker, except you would make the function either linear or somehow close to linear in some way. And the function is designed so that it returns 0 on success and something else on a failure. Then you would run an algorithm called secret sharing, or really any linear error correcting code, on the entire stack trace. And you would return these 80 pseudo-random outputs. And the argument, this mathematical argument is that because of this property called linearity, if you apply the checker to all the 80 outputs, it should also return 0 on all of them. So this obfuscation process of running an error correcting code on the stack trace actually basically sort of encodes and creates a sort of compressed form of the entire stack trace, which the verification algorithm can still work on. So why do we need to do this? Why not just pick 80 random parts of the stack trace? So the obvious problem is, well, what if I run a really big program, but then I suddenly introduce some tiny inconsistency at one particular step? If you just pick 80 random steps, then chances are you're going to miss that one step. So you have to come up with a way that incorporates every single step, and at the same time creates a proof that you can verify efficiently. So with this idea, we basically have a zero knowledge proof that works for everything. So what are the use cases of this? One is you can use anything as a mining function. So for example, phoning at home. So you can actually turn folding at home into a mining function. And the idea is that when you run the folding at home computation, you would actually simultaneously generate a proof that you ran the computation. And then that's what everyone else is going to check. Checking proofs is pretty much instant. So you don't have this problem that everybody else has to run the same computation that you did. Another application, this is called ultimate block. So actually another thing is that you don't even need to make it folding at home. If you want to be really future-proof, what you say is anyone can submit their own computation for the blockchain to run. So the idea here is that, one of the problems with doing that now is that it's possible to come up with some kind of computation which is hard for everyone else to do, but easy for you to do. So if you can convince the network to use your computation as a proof of work, then you can actually secretly be a billion more times more efficient than everyone else, and you can pretty much take over the network. With Skip, you pretty much solve the problem because you're not just providing a solution to a problem. You're providing proof that you ran certain code. Another application, ultimate blockchain compression. So here's the idea. Right now, what is a block? A block, or at least, in Ethereum, for example, a block contains the previous state, where a state is basically the balance sheet. It stores what all the states of all the contracts are, it stores what all the balances are. Then it has a series of transactions, and then it has a state at the end. So that's and in order to verify the block, you basically have to run through all the transactions yourself. What if instead I use this magic skip algorithm? So what I do as a miner is I take the previous state, I run through a bunch of transactions, get a new state, and I come up with a zero knowledge proof that here's an old state. Then I applied some set of transactions to that old state, and I created this new state, which is here. And so then the proof is efficiently verifiable. The rest of the network doesn't need to actually validate the transactions. The rest of the network doesn't even need to know about the transactions. The rest of the network just needs to know that here's a proof, and there's cryptographic magic that shows that the state transition is legitimate, which means that it's basically composed of a set of legitimate transactions. So in that case, what we have is basically another solution to scalability. Instead of every node needing to process every transaction only needs to be processed by one node. This will create the ultimate blockchain. And another side benefit of that is, so obviously transaction fees are going to drop to literally zero. But the side benefit is privacy. So with privacy basically is that if you have a transaction, you can submit your transaction just to one particular miner. That miner can include the transaction. And then nobody's going to be able to know that your transaction ever happened. The whole thing is just going to be a complete black box. No information whatsoever except what the balance changes are at each step. Finally, here's another very interesting piece of cryptography. So, yes. No, go on.
I just want, you said this approach would create the ultimate blockchain. You see that as better than all the other approaches you've presented?
Yeah. Yes, this is superior to all three of the approaches that I presented earlier. Massively so.
And why is that?
Because basically this approach, with the current blockchain, every node has to process every transaction. The approaches that I have are every node has to process some transactions. This approach, one node has to process each transaction. It's pretty much literally as efficient as you can get. It's exactly as efficient as something like as a centralized system.
And are there any significant barriers to
the fact that the math isn't complete yet?
Is what?
The math is not complete yet. It's still very inefficient. It's not entirely certain if it's even practically possible to encode some of the blockchain math into the process. So it's right. So it's basically just a matter of continuing to work on that, continuing to develop, coming up with a good implementation. So I think it's probably going to be like either 1 year, like 1 or 2 years out before this stuff really starts to go mainstream.
But my understanding is that you're hoping to get some skip stuff into Ethereum, is that correct?
Well, not into 1.0, but into 2.0, I'm sure.
Okay, very good.
Yeah. So, So the last thing I want to cover is this concept of obfuscation. So what obfuscation is, obfuscation basically does to programs what encryption does to data. So obfuscation means you would take a program and you encrypt the program to create another program which is equivalent, but which hides all of the internal data. So the ideal here is black box obfuscation. So basically, you take a program P, you create a program O of P, and then that O of P just looks like this completely indecipherable glob of math, where you can run it, and you can run it on outputs, and it produces you can run it on inputs, it produces outputs, but you can't tell anything else. So there's two use cases for that. One is if you want to hide the algorithm. So if you have some new proprietary algorithm and you want to be able to sell a program containing that algorithm without actually revealing what the algorithm is, you could use obfuscation. Another idea is you can actually hide data. So if for example I have some private key, then what I can do is I can construct a program that would generate signatures using that private key, but only under certain circumstances. And at that point, I could give out that program, and then that could basically be another way to have these kinds of right, and that could basically really open up a really large number of possibilities, which I'm going to talk about a bit later. But the problem is, though, is that it was discovered in 2008. Black box obfuscation is impossible. There's a certain class of programs that you can prove you cannot black box obfuscate. No matter what kind of obfuscator you create, you're still going to reveal a bit of information about the program. So what we've settled down on is a weaker notion of obfuscation, which is called a distinguishability obfuscation. So the idea here is take two equivalent programs, A and B. Equivalent programs meaning that given the same inputs, they produce the same outputs. Then obfuscate both of them. If you obfuscate both of them, and then given the two outputs, there's no way to tell which came from which. So is that useful? You know, it seems like it does. If black box obfuscation seems like the ultimate strong notion of obfuscation, this one seems like it's a pretty weak one. I mean, you're just saying that there's two programs that you can't tell apart from each other. So, is it useful? Well, here's a thought experiment. Here's a heuristic argument to show that it actually is useful. So let's construct two programs. One program actually contains the number 1, 2, 3, 4, 5. It contains code for a hash algorithm, SHA-3, and it outputs SHA-3 of 1, 2, 3, 4, 5. Take another program. That program doesn't contain any kind of hashing. The author of the program hashed 1, 2, 3, 4, 5 externally, and the program just contains print and then the literal text of the hash of 1, 2, 3, 4, 5. So the two programs are obviously equivalent. They produce the exact same output. Now, if we obfuscate both of them. Now we know that by the distinguishability obfuscation property, there's no way to tell which of them is which. So the argument is that from B that we know that there's no way to recover 1, 2, 3, 4, 5, because if you can recover 1, 2, 3, 4, 5 from the hash of 1, 2, 3, 4, 5, then you can reverse SHA-3, which breaks the whole point of SHA-3, and SHA-3 was specifically designed in order to be irreversible. However, since you can't recover 1, 2, 3, 4, 5 from B, then if you could recover 1, 2, 3, 4, 5 from A, that would be a way of telling A and B apart. So therefore, you can't recover 1, 2, 3, 4, 5 from A, or rather from O of A, and therefore O of A is a program which is an obfuscation of a program which actually contains the number 1, 2, 3, 4, 5, which is sort of like a private key, but from which you actually can't recover the number. So this is not a mathematical proof because all it does is it shows you that obfuscation is possible for just plain old hash functions. But theoretically, what this means is that you can probably encode secret data in other programs as well. So what's the problem with this? Well, it's really, really slow. So the current obfuscation algorithm was developed actually very recently, in mid-2013. It relies on a primitive called fully homomorphic encryption, where fully homomorphic encryption actually incurs a slowdown of a factor of 1 billion. So if you take a program and you obfuscate it, it becomes 1 billion times less efficient. Solution? Well, let's work very, very hard on it. Let's see if we can push it to at least 1 million or hopefully 1,000. Applications. So 3 of them really. So several. Contracts evaluating proprietary functions, we talked about that. Now let's talk about applications in the context of Ethereum. So one idea is, let's have an Ethereum contract containing a Bitcoin private key. It's obfuscated. And the idea is that that contract would spit out a Bitcoin transaction only if certain conditions are met. So basically what you now have is you're basically given the Ethereum blockchain control of the ability to send some amount of funds in the Bitcoin network. So basically, one of the holy grails that we've been talking about in cryptocurrency for a long time is this idea of decentralized exchange. So you can already do it one way. What you can have is you can have an Ethereum contract that can verify a proof that a Bitcoin transaction took place. But here what you could have is you can have an Ethereum contract that can actually send Bitcoin transactions. You could even go beyond this. Here's a really radical, probably impractical but futuristic example. Suppose that I have a bank account. That bank account has an online banking interface. There's a username and a password. I take a username and a password, and I put that into an Ethereum contract. I set up the Ethereum contract so that if someone sends 10,000 Ether into the Ethereum contract, then the Ethereum contract is going to initiate an HTTPS session with the bank. And there's going to be some node that's going to have to be act as an intermediary between the Ethereum protocol and HTTP to do it. But because it's an HTTPS session and it's secure, that node is going to have no power. So then over that HTTPS session, the obfuscated Ethereum contract is going to log into my bank account and it's going to send $3,000 to whoever sent me the 10,000 Ether. So you just have a decentralized cryptocurrency to fiat exchange. Obviously, probably wildly impractical, but it just shows you exactly how powerful this concept of obfuscation is. So once again, this is crazy moon math. It's right now it has a slowdown of a factor of a billion. It's probably going to take at least something like 5 or 10 years before it becomes mainstream, if it's even possible to make it mainstream. Fully homomorphic in the past 5 years, fully homomorphic encryption has gone from a billion slowdown to just a billion slowdown. So maybe 5 more years it'll go down to like 32,000 or so. We'll see. But this is the future. So basically, what the conclusion I like to make is that cryptocurrency is an incredibly powerful concept as it stands, but all the blockchain algorithms to date rely on elementary cryptography, and they rely on elementary economics. And the reality is that what we are all creating here is basically a new discipline. We are combining math, cryptography, and economics and game theory into this concept that we're calling cryptoeconomics. The economics of constructing secure, decentralized cryptographic systems that are incentive compatible and that can resist even potentially strong attackers. There exist hard problems in cryptocurrency. There exist hard problems like solving the blockchain scalability problem, figuring out how to make a good proof of work algorithm, figuring out how to make a good proof of stake algorithm, figuring out how to make a proof of work algorithm that actually incentivizes the work that's useful, figuring out how to reward human labor without creating Chinese gold mining farms, figuring out how to create a fair distribution method that, say, gives one currency unit to everyone in the world. And then finally, there's always these cryptographic challenges. Can we make skip better? Can we make obfuscation better? All of these require extensive modeling and research. Now, I think the past 3 months in Bitcoin space have made it very clear that in Bitcoin land, amateur hours is over. It's really time for people that have been in some of the researching these topics for 20 years, and people who have been working hard at cryptocurrencies for 3 years, to come together, work together, and see if we can actually solve some of these problems. If we can, cryptocurrencies are going to become much more powerful. And ultimately cryptocurrencies are going to become much more beneficial. They could have applications as an economic layer and all sorts of other cryptographic projects. Floating at home. Once we have Skip, we can make floating at home coin. Tor. There's a project that's been that actually won a prize at the Texas Bitcoin conference called Torokens, where they're trying to create a currency that you could actually use to incentivize nodes to serve as exit nodes for you. Galactic Cloud System. You know, you have to incentivize nodes to actually store your data. You know, decentralized file storage, decentralized mesh networking. What if you can earn money with your cell phone just by being a sort of micro ISP? What if you can earn money with the spare gigabytes in your hard drive? Cryptocurrency potentially has a lot of problems. Let's see if we can solve them.
Okay, guys, I think, oh, it's not working. Let's see if we can get a mic actually working. Oh, sorry. Let's see if we can get a mic to people who are going to ask questions. I think that you're willing to ask questions, so you keep your mic, and we'll just take questions as we can. So, right here in the front.
I disagree that we should have a long-term decentralized distribution. For example, Mastercoin, Ripple, and Ethereum used model when the list of people that will receive initial money predefined, and after that they can sell it. And it's actually the case for Bitcoin too, because currently when new user gets into Bitcoin, he has close to 0 chances to mine any coin, and he has to buy it from somebody else. So I believe that distribution problem is solved. Can you please expand?
Well, the distribution problem is absolutely not solved, because the thing is that, first of all, the reality is that a few thousand people hold half of all Bitcoins in existence. If Bitcoin becomes mainstream, a few thousand people will hold half of all money in existence. This is absolutely tragic on the sense that even the current monetary system does not provide. So if we want to have a currency system that people are going to be used for centuries, then we have to make it fair for people both in this generation and every other generation to come. You know, the fact that if you didn't manage to hear of Bitcoin in 2009 or 2010, then tough luck for you. That's not an acceptable way to run a monetary system. So it is basically a matter of creating a distribution mechanism that is more fair, more distributed, ensures that currency units are distributed to many people rather than only a few people, and that does necessarily mean that it has to be long term, because not everybody in the world is worth it.
Yeah, I wanted to ask, at the beginning of the talk it was mentioned about cross-chain transactions.
Yes,
but I think
solving the open problem.
Okay.
Some ideas that I had before or during the talk that I'd like you to comment on. One was like for doing proof of work that could be useful, discovering patterns in astronomical data where you can like point to a coordinate and people can check if that pattern exists there.
Sure. So it's definitely a very interesting class of computation in general. I would say the big challenge there is that that's a kind of computation that relies on a lot of data. So that's also the big problem that things like weather prediction fall into, is that you need to have some source of data for the data to come into, and you also need to verify the data.
Yeah, right. You need an authority in a sense to,
yes.
or some way to verify the massive size of data. Sure. For maintaining like the currency being non-volatile, I had an idea of like having prediction markets on various exchange rates between the currency and other currencies or goods. So you could create like a bundle of goods which ended up with, where you can like target a price for the bundle of goods in terms of your currency. And then you could, have a set of users, a set of hosts, which you can like give money to or take money from to target that.
Right. So that's basically falls into the general class of creating a stable currency via financial derivatives. It's an idea that a lot of us have been thinking of. The biggest challenge is that the price of the basket of goods still has to make its way into the system somehow.
Yeah, sure.
So you have to either trust the data feed or trust some kind of large coalition.
Yeah. I mean, I think the reason to add like prediction market on a price, and then combine that with kind of a set of authorities that you kind of trust for the outcome of the prediction market, kind of just adds a bit of integrity, because so like as in there's kind of each user that contributes to the prediction market has an incentive to sort of make their prediction in line with what the prediction market should output. This kind of creates momentum in favor of.
So not quite. So if there's a prediction market, then the people in the prediction market have the incentive to predict what the authorities are going to say the price is.
Sure.
So it's still all a matter of the authorities.
Yeah, if you so, I mean,
right. So
if you break the authorities.
yeah, so it seems to me that authorities are on some level necessary, but there might be ways of somewhat decentralizing the problem. So one interesting idea is basically to have a proof of stake system where, first of all, you would start off by all the stakeholders would figure out if you want to say decentrally, figure out what the price of gold is. Everyone would submit the hash of the price of gold. That's stage one. In stage two, everyone would uncover the price, what their estimate of the price of gold is. If your estimate doesn't match the hash, then you're obviously cheating and you get kicked out of the system. Then, of all those estimates, you first of all you sort them, and the 50% in the middle get a reward, and the 25% on each fringe get nothing. So your incentive is always to stick close to the line. So that's one of the interesting ideas, probably the more promising.
Yeah, that's cool. I mean, it's a little bit of a book. I've got like lots of ideas that I'd love to share, but
sure.
Yeah,
if you have good ideas to share, feel free to make threads about them on our forums or our Reddit. I'm sure there's lots of people who'd be interested.
When it comes to the idea of issuing N coins per person, that was something you briefly went over, but did you actually have an idea of how that might happen, or do you think that that's an unsolved problem?
It is an unsolved problem. I mean, I described the three mechanisms that might happen. So first of all, trust central authorities, then something based on discovering human labor, then something based on community reputation. And ultimately, the first and the third do sort of fall into each other to some extent, because if you have the community approach, then obviously that can sort of flow into a system where everyone trusts a few particular people, and that's when basically you're degrading into a passport system. So I think some kind of combination there might be the best we can do.
And do you think that this is something that will realistically make it into the issuance model for Ethereum?
For the issuance model for Ether, no. The reason is that we do want to have a stable base currency, or a stable, and in order for that to happen, we're already making lots of experiments, and we don't want to make too many extra experiments where a few of those might end up failing. So what I think we do welcome this kind of currency research, but if you want to do it, then do it by making a sub-currency on top of Ethereum, and then and then you can trade that sub-currency around and use it just like any other currency.
Vitalik, we've talked about this before. I guess it's sort of a broader question about the definition of cryptocurrency and what exactly qualifies. And generally speaking, we're talking about maximally distributed networks. And I'm curious if you see this simply as a linear function from a centralized network to a fully distributed network, or if there's any sort of nuance when we're talking about some things you put on early about having different node types, federalized systems, other things like that. And just my own background, I see this sort of it's important to maximize on the sort of trust of the network, but there's various parameters that lead to trust, and sort of full distribution isn't the only one.
Yeah, so the optimization objective can be defined in two roughly equivalent ways. So one way is, given a specific extent to which you're able to trust any specific person, what is the maximum? How do you define this? How do you devise a network so that you can have the maximum amount of trust in the network? The other equivalent formulation is, given a desired level of trust in the network, how do you minimize the amount of trust that you need in each individual person? So that's one way of putting it. In terms of the means, in terms of decentralization itself, there are definitely lots of strategies. You can't reduce the concept of decentralization to a number. So you could say how many nodes, but then you talk, what if you have multiple types of nodes? What types of nodes do you have? So I think, in general, we don't necessarily want to measure decentralization. We really want to think about what the security assumptions are. who are we trusting? What are we trusting?
Are there any general parameters that you would put in place to say, here, are the 3 things or something to look for when examining networks on these parameters?
Yeah. So I would say first of all, the smallest coalition size that you need to actually take over the network. So in Bitcoin, that's basically 51%. Ideally, you'd want something that's probably at least 25%. That's one parameter. Another parameter is the whole thing incentive compatible? So if people are participating honestly, are they participating honestly because that's the most profitable approach, or are they doing it as a matter of charity, or are they doing it just as a matter of, well, this is the default in the software? So obviously the profit incentive approach is probably the best. And then there are several different equilibrium concepts. Like there's the baseline Nash equilibrium, which is it's an equilibrium if everyone's acting in their interests. Then there's this concept of an epsilon equilibrium where you're allowed to let people be slightly altruistic in certain concepts. So basically incentive compatibility, coalitions, and then finally I suppose you need to look at make sure the system can survive at different. Also, future-proofness is the big one. So make sure that whatever your system is, it doesn't rely on very specific aspects of sort of the way the world is now, but relies on fundamentals. So fundamentals being things like human beings have desires and act to achieve those desires. Something like a device which can emulate a Turing-complete programming language is a general-purpose computer. Things like, but not things like this particular thing is going to remain decentralized forever, right? So basically, making your assumptions as sort of simple and also as transcultural, trans-empirical as possible.
It sounds like the upgrade from version 1 to version 2 is going to be pretty big if you get Skip figured out and put it into version 2. Have you guys talked about the issues of making a significant upgrade like that to the mining algorithm?
So what we're thinking of doing is we are going to release version 1. Version 1 is not going to have most of these problems solved, obviously. It's going to be good enough. It's going to be awesome. You'll run contracts. When time comes for version 2 to launch, with version 2, what we're going to do is we're going to pre-mine into a contract such that contract is going to pay out currency if you can prove to so that contract is going to pay out 1 ether 2, if you can prove to the contract that you destroyed 1 ether 1 in the Ethereum 1 blockchain. So you can just sort of carry your Ethereum ether over.
You guys, questions?
Yeah, in the slide where you had the mechanism where people are the source of the cryptocurrency, they're given so many per whatever year.
Yes.
Would it be possible to have some kind of a time decay on the currency such that you're giving out so much per year and then it atrophied, so if you didn't use it, then you kind of lose it? It sort of solves some of the inflation-deflation issues.
Right. Yeah. Yes. It definitely is possible. The question. Well, so the big challenge there is first of all, are people gonna? So first of all, do we really want this effect that your currency units disappear? Isn't it a legitimate thing to have a store of value where you dump something in for 50 years as savings for your children? And then the other point is that what are people going to just basically create third-party services that just ping your contract and sort of reactivate it once every 10 years? So that's all. We don't really want to encourage centralization. We might perversely end up doing that potentially. So I would say those are sort of two of the concerns. But it's a very good idea in principle, though.
Sure. I mean, one concern I have is just this idea of dynasty, right? Like if you allocate currency one way or the other, then people are born next year and they're born without it essentially. So they have to work harder to get it.
Yeah, right. That's basically the reason why I put in the linear inflation into Ether. So the argument is that exactly as much ether is going to be released during the 29th century as during the 22nd or the 21st.
Okay. Questions? Nope.
So the target inflation rate for Ethereum is judged on what sort of growth, like what's your growth projections and how does that fit?
Right. So the supply growth is going to be linear. So on some level, it's almost a sort of algorithm where there's basically nothing to decide. Like the only parameter that we're already deciding is basically what the initial issuance is going to be, and that's more of a that's not so much a long-term economic decision as a decision of how much do we need to raise the capital to grow the ecosystem and so forth. So in the long term, it's just, especially after several decades, it's just X units per year. So we aren't even making any choices. Yeah, that makes sense. Mm-hmm.
So you're still insisting that a new currency should be issued when new generation is born, but when new generation is born, let's say our planet is not becoming bigger and we're not getting more land, why this rule should work for currency? I mean, it's natural process when old savings will be transferred to the new generation by natural economic means.
The problem is so it's funny that you brought up land, because land actually is the only other major commodity aside from Bitcoin that has a fixed supply. And if you look at historical patterns in the past 6,000 years, every few centuries there's always some land reform movements to basically take land away from people who have a lot of it and redistribute it again, because it does get very concentrated over time. Yes.
Is it? Nope, just a second.
I mean, I guess this is just a comment, but isn't it new currencies are a way to redistribute the wealth? You could almost argue that Dogecoin is a new generation after Bitcoin.
Yeah, that actually is definitely a very valid point. So creating new currencies and creating new assets is a sort of way of inflating the currency supply or adding new currency units in this community-based approach without actually encoding it. Yeah, I'd say it's a matter of it's a matter of what kind of currency you're creating. Are you creating something that you want to be a standard for a really, really long time, or are you creating something where we'll pump one up every few decades for this particular community? So I think these kinds of issues, they probably matter more for coins that are intended to be sort of on the lower level and last in the long term. But yeah, if you want to create a currency that's say specific to a community, then you might not necessarily even need to care about that much.
This is about the what I asked about earlier, this ultimate blockchain approach that you're talking about. Could you summarize those steps again? Go through that.
Which approach?
You said this would make the ultimate blockchain.
Okay, so step is, first of all, I'm a miner. I have the previous state. I collect a set of transactions. So I take all these transactions. Then I run the code to process all of those transactions onto the state. So the original state could be Alice has $50, Bob has $50. A transaction is send $10 from Bob to Alice. Then the state prime is Bob has 40, Alice has 60, and so forth. So you process all the transactions onto the state, you get the new state. And then while you're doing it, you come up with this cryptographic proof using skip that says, I ran a program with the old state as an input and with some hidden transactions as an other input, and I produced a state which has this hash as an output. So you take that, so you create a proof of that statement, and then that proof is sufficiently verifiable, and then you publish that proof as part of the block alongside the new state and all the modifications to the state that you made. And then in the verification process, it's just a matter of verifying the proof.
So the details are, the important stuff is skip.
Yes. Yes.
And who created that?
The current implementation is largely developed by a team working under Ali Ben Sasson. He is a mathematician working in Israel, in the Technion. It's an Israeli university in Haifa.
Joel.
So I'm a bit surprised that you don't go into any of the crypto governance stuff besides the sort of elusive mention of consensus systems.
Right.
And I know that classically, currencies are issued by governments with ostensibly some sort of accountability mechanism for the issuers, for obvious reasons. And obviously, sort of a lot of people have looked at these decentralized platforms, including Ethereum, as this possibility of building consensus mechanisms on top of that either acts as complements or even replacements for existing governmental systems. Yeah. And I'm curious, obviously you mentioned Aurora Coin, and there's other examples of that. How you see that evolving, because it seems like one of the largest sort of areas for not even cryptocurrency, but sort of beyond cryptocurrency.
Yeah, I think it's extremely important. I would say the reason why I didn't put it in here is because the list here is more of very well-defined problems that have very specific outcomes. So, create a proof of work algorithm which has some margin, has some benefit to society, and simultaneously has the properties that it's decentralized and so forth, right? Whereas crypto governance is, and also, Charles is interested in reputation systems, which are, I suppose, a very similar area. So basically, those are more open-ended problems. So they're not in this list simply because purely for the technical, for a reason of categorization, not because I think they're less important. I would argue they're equally important, if not more important. And it's definitely something that I'm very interested in. Like the Ethereum organization itself is going to be experimenting with a lot of crypto governance in the next few years too.
Okay, well, Vitalik, could you just give us a brief few sentences on the schedule, and then maybe we'll get a couple more questions.
Okay, schedule. So we're hoping to launch the Ether sale very soon. So like probably 2 weeks. Well, I don't want to promise anything, but it is looking closer, like it's coming closer and closer. Then development. So POC 3.5 should come out very soon. And then at that point, it's something like half a year on to basically finishing through the entire development process, releasing Ethereum 1.0. So we're hoping to have that we're hoping for late summer. We'll see. It might drag into the fall. Then Ethereum 2.0 is going to be something like around 2016 or so, turning the Ethereum organization into a DAO probably at the same time.
Okay. And let's say there's some guys that want to participate more. They have some questions. How would they? Could you give me some contact information?
I actually put up the contact information on the last slide.
Maybe you can just tell us.
Yeah, Vitalik@ethereum.org.
Okay. And if you forget that, you can send an email to me. It's on the meetup page, Christian Peel. I'm on the meetup page, christian.peel@itriple.org. That's another route. Any final questions? Oh, please. Just let's wait for the mic.
What are your thoughts about how Ethereum will be funded and how this will turn out for the people that will be involved, considering all the ideas you have?
So the funding for Ethereum is, once again, we're going to have the Ether sale where we'll be selling some units of the currency in a few weeks. So that will basically be the bulk of our initial funding, plus a certain reserve of Ether, which we'll keep for the long term. And then later on, it'll probably transition to a model where we're more dependent on various kinds of applications and services on top of the platform.
So are you pre-mining? How much?
Yes. Well, the pre-mine is basically so there's a certain amount pre-mined, and then about 30% of that will be released every year through mining forever.
How much is pre-mined?
Well, it depends on how much people buy. It's a scaling model, right? So if people buy 10 million units, then 3 million units get released a year. If people buy 20 million, then 6 million get released per year. So it sort of doesn't matter on some level.
Okay. Let's thank Vitalik. So Vitalik, I guess you'll be around here for a few minutes if people want to ask questions. All right, thank you very much, folks.